even if you are having a positive charge on this nitrogen, even if you are having a positive charge on this nitrogen, remember that this bond electrons are moving only towards the oxygen. This is not getting attracted towards this positive charge. Why? Because oxygen is more electronegative than nitrogen, and hence the bond will break heterolytically only to the oxygen atom. Okay, so that will make this nitrogen double positive. So these pair of electrons is attracted towards this nitrogen. So what is the result of that? The result is the electron density in the benzene ring is reduced because it has gone into the nitro group. See here, these pair of electrons here, this pair of electron has gone to the nitrogen atom, creating a positive charge inside the benzene nucleus. Now this positive charge is getting delocalized. So from here, from this position, it is going to this position, and from here it is getting spread all over the ortho positions and para position of the benzene ring. Remember, this is called ortho position. These two are ortho. And this is a para position. So the positive charge is delocalized in this locality. Now what is the result of that? What is the result? The result is the more concentration of electron is on the meta position. There is no change for the electron density of the meta position. Look very carefully. This is a meta. No change in electron density of this position in any of the structure. Okay. But ortho position is electron deficient. Ortho position is electron deficient. So this is the effect. Similarly, you can draw the resonance structures of other compounds, like see here, benzene sulfonic acid. See this. Now look at the sulfur. Sulfur is more electropositive than oxygen. Therefore, the electrons are attracted towards the oxygen atom. And you can see here, the sulfur is highly electropositive here, delta positive. Here, delta negative. Here also delta negative. Here also delta negative. And this cumulative effect, combined effect, will make this highly electron density electropositive. Delta plus plus plus. Okay. Now see here. The same way as we have drawn here, we started with this. Similarly, you start with this. Do the same thing. See here, this pair of electrons is moving towards this nitrogen. Similarly, do the same thing here. Now draw all the resonance structures of this molecule now. You get the first one. Double bond S, single bond oxygen, double bond oxygen, and NOH. Sulfur is having same number of bonds over here, with a positive here. Now this positive can be delocalized as we have seen here. It will come to this place, You can draw it again. It will come to in the next structure. It will come to this place. Okay. And one more structure you can write. That's the last structure, and that will be the last structure will be this one. A structure in which the double bond have changed the place. The double bonds have changed the place. That is going to be the last structure. Okay. So this is what we call as resonance effect. Right. So this is so we have discussed the inductive effect. Did we do it? Inductive effect. Hyperconjugation. Hyperconjugation and resonance effect. These three are the main electronic effects affecting the reactivity of different compounds. Now, basically, let me discuss with you some consequence of this inductive effect on acidity of carboxylic acids. Acidity of carboxylic acid. Acidity of carboxylic acid affected by inductive effect. Did I mention that? I don't know. I don't remember. To be specifically, I have mentioned. I don't think. Let's see. Now see here. Let me write CH3 COOH. CH3 I will write here. C double OH. And then I take another compound. I replace one of this hydrogen with a fluorine atom. Two hydrogen with a fluorine atom. Three hydrogen with a fluorine atom. So this is trifluoroacetic acid. This is difluoroacetic acid, it's monofluoroacetic acid, and this is simply acetic acid. Now, how is acidity? What is acidity? Look at what is acidity. Acidity is ability to donate electron, release electron. Ability to release electron. Proton. Sorry. Donate a proton. That is your acid. For example, this is the acid. This should react with water and should give you and H3O plus. If the equilibrium is shifting more towards the right hand side, towards the product side. If the equilibrium is shifting more towards the product side, it's a strong acid. But if the equilibrium is remaining on the starting material side, the acid is a weak acid. So the strength of the acid can be described in this fashion. That is, a strong acid will react with water and completely release the protons. 100% release of protons. Okay. But in this case, this is an inorganic organic acid. Organic acids are supposed to be weaker than mineral acid. Why? Because if you take organic acid and put in water, 95% will be in the undissociated form. Hardly 5% will be getting dissociated. And that is why we call it as a mild, a weak acid, not a strong acid. So only 5% will be remaining dissociated. Now, in this acid-base reaction, the criteria for acidity are two. The criteria for acidity are two. One, ability to release a proton. Ability to release a proton. Release proton. Okay, two criteria. Second one, stabilization of the resulting anion. Stabilization of anion. Okay, now this is the anion. This is the anion. The question is stabilization of this anion. See here, how can you stabilize this anion? CH3, CW14, 4 minus. How will you stabilize this anion? Delocalization of charge. Delocalization of charge. That is the criteria for stability. How can you delocalize the charge? See on this 3 pair of electrons. Now see, delocalization. That means the oxygen, the charge on the oxygen is getting spread to the other oxygen also. So in a very simple way, see here, let me explain to you a very simple way. Now the ability to reconvert it back, the more it is getting reconverted, the H3O plus will be removed from the system. That means after ionization, there is a tendency for these opposite charges to combine and go back. If you prevent that recombination backward, that compound will be a strong acid. They should not combine. Once they are combining, then the proton is already trapped inside. Here, an acid is a substance which will release proton, not trap proton. So, this backward reaction should be prevented. Assume the H plus ion is coming closer to this. H plus ion is coming closer to this ion. What happens? H plus will have, sorry, H plus. It will have a tendency to attack the oxygen which is negatively charged. But the moment it reaches here, probably this double bond, the electron flow away from this oxygen towards the other oxygen. So it reaches here. Then now this H plus will go to this oxygen to get combined. but by the time the negative charge has reached back. So sort of musical chair is occurring here. Okay, that is why this resonance effect is making the carboxylic acids, making the carboxylic acid act as acids. That is, the release of proton from here will result in the stabilization of this anion. Okay. Now, suppose I put a fluorine atom here on this one. See here, I put one fluorine. H, C double bond, OH. Now, what is the result? O minus. Now, this is already flowing in this direction. Already this mesomeric effect is there. Along with that, look at the inductive effect. These electrons are attracted towards here. This will be attracted towards this side. What is the result? The result is electron is getting delocalized over to this side also. Negative charge is not getting delocalized here only, but it is getting spread all over. It is getting spread at this point of delta plus. Okay, so there is delocalization of the electron, and that will lead to stability. So this is more stable. Suppose you replace one more fluorine, it will be still more stable. This is more going to be stable. And if you have one more hydrogen fluorine, that will be still more stable. Okay, so this will lead to this is how the inductive effect is having a role in the acidity, deciding the acidity of the organic compounds. Okay, so in fact, see here, trifluoroacetic acid is the strongest organic acid. CF3COOH. Okay, this is the strongest organic acid. Clear? So this is the effect of inductive effect. How it is affecting the acidity of organic compounds. Right? So this is basically the different effects. Now there is one more effect known as steric effect. Steric effect. Steric effect is due to steric effect means change in reactivity due to bulkiness of groups. Change in reactivity or change in property. Due to bulky groups. Okay. See, for example, look at this molecule. Look at this molecule. H. This, what is the name of this molecule? 1, 2, 3, 4. So 4 carbon, it is butane. 4 carbon is butane, but you have a double bond between 2 and 3. So double bond means what? You will put a E, change the name from A to E. Okay. Now where is the double bond? 2 butene. So cis, this is, and you can see here the CH3 groups are on the same side of the double bond. So you will call it as cis. You have a corresponding material, a trans molecule, CH3 and CH3. You have a trans material, trans 2-butene. Butene. Now see here, these two molecules, they have difference in property. They have quite high difference in property. What is the consequence? See here, these two are bulky groups. CH3, both the CH3s are bulky. Why you say bulky? See here, you have a hydrogen here, you have a hydrogen here, and you have hydrogen here, and hydrogen here. So there is an interaction between these groups.